All right, so for question 2, we're asked to compute each geometric sum. So for part A, we're looking at the sum of 2 to the n as we let n vary from 1 to 5. And so this you could easily do just by hand, but nonetheless, we'll go ahead and compute this sum using that formula we derived in the last video. So here we're looking at 2 plus 2 squared plus 2 cubed plus 2 to the 4th plus 2 to the 5th. All right, so note here, A, the first term is 2. R, the common ratio, is also 2. And we're summing a total of 5 terms. Okay, so then that formula we derived in the last video, we take A, which is 2, times the quantity 1 minus R, which is 2, raised to the n, where n here is the total number of terms we're summing. So 1 minus 2 to the 5th in parentheses, and then downstairs we have 1 minus R, so that's 1 minus 2, and that gives us a sum of 62. All right, for part B, we're looking at the sum of 1/3 raised to the k power, and we're letting k vary now from 2 to 7. Okay, so we're looking at 1/3 squared plus 1/3 cubed, all the way up until we get to 1/3 to the 7th. We can apply that same formula just as we did in part A. So to do that, A there, the first term, 1/3 squared, that's a 9th. R, the common ratio, well, we're just multiplying by 1/3 to get from term to term in the sum, right? So R is a third. And here we're summing a total of 6 terms, right? So K, the index varies from 2 up to 7. So that's a total of 6 terms we're summing. So the sum then will equal A, which is a 9th, times the quantity 1 minus R, so a third, raised to the number of terms we're summing, so raised to the 6th power, all divided by 1 minus R, so 1 minus a third. This is a little bit messy to simplify, but as a simplified fraction, it's 364 divided by 2187. And an approximate form, that's 0.1664, okay, rounded to 4 decimal places. Okay, so how about part C? We're looking at a series now, right? It's an infinite sum. And we're looking at summing 2 to the n as we let n vary from 1, well, to infinity. Okay, so in part A, we summed up the first 5 terms of the sequence 2 to the n. Now we're going to add up all the terms of the sequence 2 to the n. If you give that a little thought, we're looking at what? 2 plus 2 squared plus 2 cubed, so on and so forth. Is this going to be a convergent sum? Is this going to give us something finite? The answer there is no, right? Now, we argued in the last video that for a geometric series like this, we'll only have convergence provided the common ratio R is strictly less than 1 in absolute value. Now, R here is 2, right? And since 2 is more than 1, right, this series will diverge. You can also just see that by thinking about what's going to happen to these partial sums, right? We're looking at 2 plus 4 plus 8 plus 16 plus 32, so on and so forth. Clearly, those partial sums will approach infinity, okay, and so we get a divergent sum. All right, now for part D, we're looking at, again, a geometric series. In this case, it's 1/3 to the k as we let k vary from 2 to infinity. So again, it's just extending what we saw in part B. I'm going to sum up all the terms now of this sequence. So 1/3 squared plus 1/3 cubed plus 1/3 to the 4th, so on and so forth. All right, so A, the first term, that's 1/3 squared, that's a 9th. R, the common ratio, is a third, just as it was in part B. And what we argued in the last video, right, is that for a convergent geometric sum, which this, by the way, does converge because our R value here is a third, and that is strictly less than 1 in absolute value. So for a convergent geometric sum, okay, we take A, which is just the first term of the sum, so that's a 9th, and then we divide that by 1 minus the common ratio. So 1 minus R, so we get 1 minus a third downstairs. Now that simplifies to a 6th, which is approximately 0.1667 rounded to 4 decimal places. And notice that it's just slightly larger than our answer to part B. Okay, now it makes sense that these are relatively close. And what the fact that this is so close says that really these tail end terms, so 1/3 to the 8th and so on, they're just not going to contribute very much to the sum. Okay. All right, very good. Well, that does it for question 2. Now, question 3 is a fill in the blank, and it's really stuff we've already discussed, but just to go over this really for emphasis, it says the geometric series, so a plus ar squared, so on and so forth, which is written here as the sum of ar to the n as we let n go from 0 to infinity. This will converge when, well, again, the common ratio r is strictly less than 1 in absolute value. And for those values of r, okay, the sum of this convergent geometric series is a, the first term, divided by 1 minus r. For all of the values of r, the series diverges. Okay, we get a convergent sum for r strictly less than 1, and the sum is a over 1 minus r. For all of the values of r, the series is divergent, just like we saw in part C. All right, well, that's going to do it for this video. In the next video, we'll look at yet more examples of geometric sums. All right, thanks.